hope everybody can hear my voice. Anyway, so these slides will show you a general list of items that need to be followed to design a test facility, to operate a test facility, how to set up an experimental campaign. So, okay, so in general, I will speak about why do we need experimental facilities, and why we need an experimental facility in the frame of the ELSMOR project, and how to design experimental facility with particular attention to the facility for ELSMOR. So the speech is general, but with details of about the ELSMOR facility. Then I will speak about the scaling of a facility, the mechanical design, the instrumentation and data acquisition system, how to do testing, data analysis, and code validation. So these are the main topics of this speech. So why do we need experimental facilities? When we go toward the certification of a new nuclear power plant, in this case we are speaking about small modular reactors. Thank you. Different systems and components need to be tested before the plant obtain the certification by the main body, the regulator, I mean. So we may have different kind of test facilities. Some facilities are called separate effect test facilities that are devoted to test specific components, while we have integral test facilities that are devoted to test the whole system. So they can simulate, for example, the primary side, the secondary side, in some cases also the containment of a whole nuclear power plant. And another goal is of operating test facilities is to collect experimental data for code qualification, code assessment. And so these codes will be used for the reactor calculations when the final certification of the reactor is asked. So in the ELSMOR project, we are going to build, well, we are building now an experimental facility that is a separate effect test facility, because it is devoted to test a decay heat removal system that includes a natural circulation loop with 2 heat exchangers that are adequate to reject the decay heat of the reactor into a water pool. And at the end, the experimental data will be used to validate computational codes. So, in the specific, for the ELSMOR facility, the design include a new type of heat exchanger that hasn't been used before for civil use in the nuclear power plants, and it is a type plate heat exchanger. So the ELSMOR facility will include such kind of heat exchanger to represent or to act the heat transfer from the primary side to a natural circulation loop that also includes another heat exchanger immersed in a pool standard type with vertical tubes that rejects heat to the pool. So, in general, the design of the facility includes many steps. First point is a technical specification. So when we design a facility, we need to have a technical specification that says what are the goals of the testing. We need to know what we are going to do. An indication of the scaling factors, because it is very important to have adequate scaling factors to reproduce the specific or particular phenomena we are going to investigate. In particular, we speak about elevation scale, volume, and power scale. Then the specification should include which phenomena are of interest to be analyzed in the simulation, in the facility, I mean. And also it specifies the instrumentation that is needed. In general, it is in terms of points of measurement. I don't know, for example, we want to measure temperature at this position, at the other position, and so on. And also the characteristics of the data acquisition system. And last but not least, the test metrics. So test metrics is a list of tests that need to be performed in the facility. For the ELSMOR facility, we have proceeded to scale down this natural circulation loop from the characteristics of the European SMR that are that has an electric power around 170 megawatt, thermal power 515 megawatt, about, and it has two loops of emergency heat removal systems. So in this case, it needs these heat removal systems need to discharge about 60 megawatt in two, so about 30 megawatt each. So we have scaled our facility to have a power scale on this data of about 1 to 50. That is a very large scale for a facility. That's true that this is a separate test facility, so we may have a larger scale than we should have in an integral type test facility. But anyway, 1 to 50 is a large scale. And we have an elevation scale 1 to 1. So we reproduce the full elevation of the real system, because in particular in this case we focus our attention on the natural circulation in the loop. So it is very important to reproduce the gravity heads and the driving force that will be present in the real plant. Other values we had from the specification were the pressure drops in the heat exchanger, because the heat exchanger, the type plate heat exchanger, had some pressure drops specified, both primary and secondary side. So we tried to reproduce those drops or to find a heat exchanger with similar pressure drops. So just to have a look of a simplified scheme of the facility in order to understand what we are speaking about. So we have a primary side. In the facility, it is represented by an electrical heater, a pump that circulates water, and a tank, a vertical tank that okay, I thought, because I saw the mouse here. Thank you. So here we have an electrical heater, a pump that circulates water. So this hot water goes inside this tank that may be used in two ways, or full of water, or in two-phase conditions with steam and water. First, let's speak of water. So the condition of full water. So we will have this loop that represents the primary side of the reactor. This is the type plate heat exchanger. So the primary side enters this side and circulates here. And we have a natural circulation loop on the secondary side that heats up, boils water, steam enters this heat exchanger immersed in a pool, water, steam condenses, water go back, turn here, and so on. So this is the natural circulation loop. And what we are going to verify is that this combination of type plate heat exchanger and vertical tube heat exchanger and the whole loop, that if they are adequate for this goal, to remove the decay power from the reactor. Okay. In detail, we had some specifications for the type plate heat exchanger. So it was they were specified the operating conditions, both on the primary and secondary side. The design conditions, the operating conditions, and so water and flow rate of water and both primary and secondary side were specified, and also pressure drops. We had some dimensions for it and the nominal power to be transferred. This is a custom component, difficult to be realized, and so the decision was taken to go toward a commercial type plate heat exchanger. You can see it in these pictures. We have just received it from a manufacturer. And so in this table, we have the characteristics of this component, that it is different in dimensions in terms of height, but from all the other points of view, pressure drops, heat transfer capability, it has adequate characteristics to be included in our testing loop. So we have procured this component, and what are we going to do? It has 8 nozzles, 4 on the primary side and 4 on the other side, and we will use 2 of them for the loop to circulate water, and 2 of them to insert thermocouples or pressure taps inside, in order to have an adequate characterization, or hopefully as much as we can, characterization of this component, because we bought it from the market and the manufacturer didn't give us the real characteristics of the component. But we will investigate on the testing side. So we also did a verification for this component, because we didn't know anything about it. So we interacted with the manufacturer to better understand if its capability to transfer the power from the primary to the secondary side of the loop. So we asked the manufacturer to perform with their calculation code with which they dimension the heat exchanger to perform some calculations, such that we could determine or estimate the heat transfer coefficient. So we started with a symmetric case. We asked them to perform a calculation. And so he gave us the transferred power, the delta T logarithmic mean. These are the characteristics. So at the end, he gave us a total global heat transfer coefficient. So we knew we had liquid both sides. We knew the power. So we knew the characteristics of the material, the thickness of the plate. They were declared in the data sheet of the component. And we got the heat transfer coefficient liquid side. Then we asked him to do other calculations. So with a superheated steam case, so on the secondary side. So we had liquid side on the primary side and superheated heat on the secondary side. We used this coefficient at the liquid position, and with the global heat transfer coefficient that he gave us, we obtained the heat transfer coefficient for the steam side. Then we asked them to simulate the standard case we are going to experience in the facility. So we have liquid on the primary side and evaporating steam in the heat exchanger. So with the heat transfer coefficient got from the previous passages, we found also the heat transfer coefficient in evaporating conditions. And also, we had also a case with the primary side in condensing condition and the secondary side in evaporating conditions. So we had an estimation of all the coefficients for these conditions. And we saw that they are values that are reasonable. So they are values that we can also find in the literature for these kind of components. And so they, it seems it works for our case.
Sorry, Roberto, may I interrupt you just 1 second? Do you think that it is reasonable that with liquid you have 5,800 and you have something less with liquid and evaporating?
I think it is. I don't know. Actually, this is what we
this is what they gave you.
Yeah, yeah.
So
this is they gave us these values. They dimension those heat exchangers with a code, and they sell them. So we think they are.
You will test.
Yeah, we will test.
Understand.
We will test.
Reality.
So in here we have some details of this heat exchanger. We go a step back. We received it without any flanges, so with just these nozzles. But we are going to modify it by welding some flanges for the connection to the loop. So this is a drawing that has been given to the shop to go ahead to proceed with the manufacturing. Okay. And in here we have the data sheet of the component that includes all data that are useful for us to proceed. So In this slide, you can see the position of this facility on an existing load-bearing structure we have at SIET. Because when we design and build a test facility, we need a place where to put it. Because when we work on the paper, everything seems easy. So, okay, we design a facility, piping, but when we need to build a facility, we need to find a place, to fix it to the beams, to sustain, to make verifications of the structure, to support the weight of the facility, and so on. So at SIET, we have a big structure that contains other facilities. Now you see it empty, but tomorrow when you will be at SIET, you will see a little different situation. Anyway, this is the structure where this facility is going to be placed. We have an electrical heater, a big electrical heater, 10 megawatt power. For our testing, we will use about half megawatt, 600 kilowatts. But for other plants that are installed in this area, we use the full power of the heater. So here we can see our type plate heat exchanger connected to the primary side, this part, and to the secondary loop in natural circulation, this side, with the pool. This pool is located at the top of the structure. And we have the heat exchanger here, and let's say the primary side tank here. Then we have other piping that are not represented in this slide that go to the pump and go back to the electrical heater. We have already existing infrastructures. So the things we are going to do is to connect this new loop to our infrastructures. And this is relatively easy for us because we already have very big infrastructures and so only new parts are going to be installed. Here is just an example of drawing we have prepared for the fabrication of the components. So in this case, this is the primary side component. And we have examples of piping drawings. So the piping that go to the heat exchanger and go back to the heater. So I don't go into the details of these drawings. I have reported them just to give an idea of what is behind the fabrication of a test facility. Here we have the drawing of the vertical tube heat exchanger. We have the drawing of the pool. And here instead we have a sketch of a nodalization prepared for the RELAP 5 code that simulates our loop. Why did we do this simulation? Actually, ENEA did this simulation for us because when we were designing the facility, first we did a guess of tube diameter and tube layout with bends, with elbows, valves, orifices that are all installed in the facility. But before proceeding with the fabrication, we asked ENEA to do a simulation with the RELAP 5 code to verify if the diameters and the layout of our loop was reasonable, or if the code simulated some, I don't know, some issues that we might have in the plant. And actually, we have had with them a feedback, some very interesting feedback on the piping diameters and the piping pressure drops that led us to increase the size of the pipe. Because with the size we had established at the beginning, we had too large pressure drops. And so the natural circulation didn't occur, or occurred very slow, that was not sufficient for our goal. So these code simulations helped us to improve the design of the facility. Just an example of what they simulated. We have a test matrix. I will speak about it later, but a test matrix is a list of tests to be performed in the facility. So here I report an example of results of the calculations that ENA did that concern a test that has a primary circuit pressure, specified pressure, a primary circuit temperature, so the initial temperature, then temperature increase, then temperature decrease, decrease more, and increase back. So we have specified the primary side flow rate. We have the conditions of the primary side, so one single phase. We have the flow rate of the secondary side. Well, I mean, I go a step back to show you better understanding this. Okay. We have two primary side flow rates. We have a total flow rate that circulates through the pump, and we have another flow rate, smaller one, that goes inside the heat exchanger. And such flow rate is obtained by means of a flow restrictor inserted in this tank and the actuation, the position of this valve that determine pressure drops, a differential pressure between this part of the loop and this part of the loop. And so we have two flow rates because we cannot run the pump at 3 kilos per second because we have, these are very big pumps. And so we need to circulate a sufficient flow rate for the pump, but we need a small flow rate in the heat exchanger. So these pressure drops, artificial pressure drops in the loop have been inserted to have an adequate flow rate. So this is the reason why we have the total flow rate in the primary side and the flow rate that enters the heat exchanger. Then another important factor in this loop, in the natural circulation loop, is the filling ratio. How much water do I need to include inside the secondary loop? We don't know now. So we will do different tests with different amounts of water in the secondary loop to find the best filling ratio for the plant, for the loop. So this test has been performed with 30% filling ratio. Then we have a secondary side initial temperature. We start from cold conditions, then we will see which will be the temperature, the reached temperature. We have the temperature in the pool, temperature of water in the pool. we have the level in the pool. So we will start the test with the full level in the pool. Then water will boil and will evaporate. So at the end, we will have a lower level. So we will test the capability of the system to remove the decay heat also with a low level in the pool. This means that part of the tubes of the vertical tube heat exchanger will be uncovered, so steam will not be condensed in that area. We may have also other parameters that can be set in the plant. For example, we have a measurement orifice for flow rate at the outlet of the vertical tube heat exchanger that introduces some pressure drops. The heat can be changed. So we have also, another flow orifice to set pressure drops. In this case, the ratio, that's the ratio between the hole of the orifice and the pipe diameter, is 1 in this case. So this means there is no orifice, but it could be 0.5. This means we will introduce a restriction in the pipe that increases pressure drops. So this can change the circulation and the flow regime in the loop. And we have also valves that can be closed or kept fully open to study, to change the pressure drops. So part of the test will be also focused on this aspect. So this is just to say that the test that has been simulated by ENEA includes all these phases. And here we have an example of the results that have been obtained, where the code has provided the trend versus time of quantities of interest. For example, we have the primary circuit temperature, the blue curve, so it reproduces the curve that we established in the test metrics. We have the two flow rates in the primary circuit. Then we have the type plate heat exchanger. In this case, we have the flow rate, and we have the pressure at the outlet. This is on the secondary side. Here we have a picture where the transferred power is reported. So we see that actually the code simulates the transferred power around 600 kilowatt. That is more or less what we were expecting to have from this heat exchanger. And power doesn't decrease much at the different conditions that are established. Obviously, when the primary circuit temperature decreases, also the power decreases. When it increases, okay, it increases. But when the pool has a low level, well, power is a little lower. So here we have an example of code, of the results of the code that helps us to do testing, because we have an idea of what to expect. In general, there is always I don't know how to say, a contrast between code users and people who does experiments. So, but I think that both these aspects are fundamental for an experimental activity, because codes, even if they can make some mistakes or have some correlations that are not able to exactly reproduce the real physical phenomena, they give important information for the conduction of an experimental campaign. So thanks to ENEA for this simulation. Okay. Now, once we have defined the loop, the iron, I mean, the steel, piping, and so on, we need to proceed to the choice of instrumentation and data acquisition system. Okay, so concerning instrumentation, how do we choose instruments for an experimental facility? We have some basis to define the instruments. First is the measurement range. We know how much is the about the differential pressure between points in the plant. So we need to choose some differential pressure transducers adequate to measure that differential pressure. So the measurement range is fundamental. Then another parameter to choose an instrument is the instrument accuracy. In general, we look for very accurate instrument, but there is always a balance between cost and needs. So, and also the reliability of the instruments, because if we do a test and an instrument stops working, we lose the point. So reliability is important. And these instruments, before being installed on the plant, need to be calibrated in a calibration laboratory. So at SIET, we have a calibration laboratory. We are lucky. It calibrates instruments for us, for our facilities, but it also calibrates instruments for the industry. But anyway, when we need the calibration, it is very fast. We disinstall the instrument from the plant, take to the lab, they check and give it back. And we have a calibration certificate. So every time an instrument is calibrated, a certificate is issued. This certificate includes some data that give us an indication of the accuracy of the instrument. So they inject, for example, a reference pressure from a primary standard in the lab, and they read what the instrument gives. So if these values are very similar, the instrument is okay. Otherwise, we need to change the instrument. So in here, I have put an example of instrument table for a facility. Here we have the full table. It can be opened. I don't know if Marco distributes the presentation. Anyway, I don't go through all the instruments. In here, I have just an example of the content of the instrument table. So we have the location of the instrument. Where is it? So, and what's its function? The type of instrument. So if it is a differential pressure transmitter, or a relative pressure transmitter, or a thermocouple, different kind of instruments can be installed. The manufacturer of the instrument, the model of the instrument, the plant code, because every instrument in the plant is identified with a code. So when we record data by the data acquisition system, we have a file, a list of variables that represent all the instruments. Then we have the identification of the pressure taps, because the instruments are connected to the process by means of pressure lines, in the case of pressure instruments. And so each pressure tap is identified. Then we have, for example, if we have a differential pressure instrument, we have two taps, which is the high pressure taps and which is the low pressure tap. So they must be identified. We need to know which are the taps. And so the table summarizes also this information. We have the elevation of the taps, we have the elevation of the instrument, and we have the measurement range, the lower value and upper range value of the instrument. For example, in this case, this table is not complete because we are still defining. But anyway, this is an example of instrument table for an experimental campaign. In the ELSMOR facility, we have about 150 instruments. And one part that is heavily instrumented is the pool, because data will be used for CFD assessment of concerning the pressure distribution inside the pool. Then we have a data acquisition system, because we need to record all the signals from the instruments. How is it done? At CIET, we use, in general, national instrument components and LabVIEW Ambient, still from national instruments, to develop the software for data acquisition. So this is an example of data acquisition system. We have chassis that contain data acquisition boards, and these boards are different depending on the signals they are going to record. So we may have boards to record high-level signals, I mean 1 to 10 volt, or also low-level signals, plus minus 50 millivolt, because different instruments provide different signals. We have pressure and differential pressure instruments that are recorded from 1 to 5 volts, so high level type, and we have thermocouples that are low level signals. So this is an example of data acquisition systems, and at the back of each of these boards there are pins, and the cables from the instruments are connected to all of these. So there is a big work of cabling, of cable routing from the instrument position to the data acquisition position. And then data are sent via Ethernet to a computer, and that is in the control room. We have a control room where there are some controllers to control the facility, I mean to run the pump, to heat up the electrical heater and so on. And we have a computer that does the data acquisition and control the thermohydraulic parameters. The software does more actions, acquires the voltages, then converts the voltages to engineering units, for example, kilopascal or megapascal, depending on the instrument constant that arrives from the calibration certificate. So we know from the calibration certificate how to convert voltage to kilopascal, for example. Then the software is set up also to obtain derived quantities, because we can measure a differential pressure, but we want to know the flow rate. So there are specific formulas and routines that transform a measurement of differential pressure into kilos per second. So at the end, we have a file of data that includes all the variables we need. Here is an example of process and instrumentation diagram. This is an example for the ELSMOR facility. So we have on this diagram the loops. We have the natural circulation loop in here, and we have the primary loop in here with all the circulation loop that contains the pump and so on in here, and all installed into instrumentation. So we know exactly where instruments are located. This is just to give an example of process and instrumented diagram. The test metrics. So the test metrics has to be defined on the basis of different requirements. For example, the first one is what we want to see, which phenomena do we want to investigate in the facility. So this is important to define it as metrics. Then also we can define the test metrics in order to optimize the facility operation. Another item that can be useful to define a test metric is if there are specific needs for code validation, need of data for code validation. And also another point that in general needs to be checked is the cost of energy. In this case, we haven't a very big energy to be used. They will be less than 1 megawatt. But in case we have, for example, other testing at 10 megawatt, when we do testing, for example, in this period we are doing testing for another company, and we take from the grid 14 megawatt power, we use half power of the whole city of Piacenza. So when we start up our plant, the national body for the energy calls us. This happens often. So then just a few words to conclude this speech. When we do a test, the first thing to do in the morning before starting is the check of the instruments. We need to check that all the instruments at cold conditions, still water, they measure 0. If not, we need to go and check, because there might be something wrong in the instrument or a pressure line that is empty. And so this is the first, and we call it hydro zero check. Then, after we perform the test, the first thing to do is the data analysis and check if the system has circulated as we expected. So we do this analysis, and then data are used for code validation. So with the codes, there will be post-test analysis, and so the results of the code will be compared with the real experimental data. And this is the most funny part of the job, because we always find something that is not that does not match, and so we need to go and investigate the reason. And another part that is very important in an experimental campaign is the schedule, the time schedule, because this is an example of time schedule for the experimental activity in the ELSMOR project. And we have a specific time to realize the plant, to perform tests, to prepare the data report and proceed, provide data to those that will do post-test calculations. So this is an overall view of an experimental campaign with a specific example to the ELSMOR project, but yeah, if you have any questions, I have nothing more to say.
Thank you. That we understood that it's not so easy to manage an experimental facility. I think that we have time for a couple of questions. If you have, please.
When one is too big, we can stay 1/1 in the height. But from the point of view of power and volume, 1/1, if we have, let me go back to the. So, if we went 1/1, we should have about 30 megawatt power available to do the test. And this is not feasible, at least for us. Maybe there are some labs that have such power, but I don't think so, because we are one of the laboratories that have more installed power in, I would say, in the world. So this is the reason why we absolutely need to scale down with power. Power and volume, they are correlated, but we maintain full height because the gravity heads are the same, even if you have such big pipe or this one. In the height, you have always the same driving force. This is the reason why.
So this is, I would say, a classical rule. If you want to test the natural circulation, you cannot scale natural circulation. So you have to keep the full height in order to test that really the driving force is that one. You can scale down the volume, the power, the transfer, the pressure drop, the surface, the pressure drop, yes, but in order to test a passive setting system, typically the requirement is to keep the full height.
Yeah.
Please.
How do you decide which projects to take up on for testing? Like which project to test? How do you decide?
It depends. For example, the ELSMOR project included an experimental part, and the goal of this kind of testing is to show the European regulator how it is, how an experimental campaign has to be conducted to provide experimental data useful for an eventual SMR certification in Europe. And in this case, the safety system for the ESMR is dedicated removal system, so it was decided to do this kind of testing. But in other case, we at CIET, we receive, we are asked by companies, for example, that design nuclear power plants or apply for certification. An example, in the last years, in the last 10 years, we have been doing tests for NuScale power to characterize their helical coil steam generator. They are developing a small modular reactor in the US. They are relatively ahead in the process. And we have done this characterization starting from 3 single helical coils up to a very big heat exchanger with around 300 tubes, very big dimensions. I mean, 10-meter high and 2-meter diameters to test heat transfer. It was immersed in a vessel, like a real vessel, flown with hot water at high pressure, primary side, and water, secondary side, and so heat transfer was characterized. Then another activity for them, for the characterization of this steam generator, we have partially done, and we need to conclude, is the investigation of the mechanical behavior in terms of vibration frequencies, natural frequencies. So we have built another heat exchanger, fully instrumented with accelerometers, strain gauges, and so on. And we have done tests of vibrations. And for the moment, we have done tests in air, but we will do tests also in water. So we have different customers that come to us and say, hi, I would like to test this. So can you build a test facility? And so we interact a lot with them up to define a testing loop and tests.
But
yeah,
who is saying to the company, you should test this item and not that item? Sure. So it is the interaction with the safety authority that suggests the company, the vendor, okay, probably it's better if I build an integral test facility, a separate effect test facility for this and this and this component. So it's from the interaction with the safety authority that this need emerges. So am I correct, Sean?
Yeah, it's usually a discussion with the regulator, where again it comes down to how proven is your design, where are the areas that you're not as proven as you should be. So it is a discussion with the regulator. It's not the regulator that says you need to test this, but it's certainly, safety analysis will show where there's not enough certainty here, so we need to do more testing.
Yeah. In fact, an example for us has been in 2015, we did a lot of thermohydraulic testing for NuScale for their application. Then NRC told them, hi guys, you need to deepen more in detail this aspect. So they have come back to us. And now we are doing more tests specifically to investigate some aspects of their component to give an answer to the regulator. So we don't discuss directly with the authority, but
and also, Sean, please correct me, but the regulators are not so prescriptive. They are not saying you must do the facility in this way to test this test method. No, they say we need to explore more this area that we don't know yet. Yet we don't have an evidence that this issue, that is up to you to discuss with the CA to elaborate what type of facility, what type of ranges of scaling factors, of size of the test metrics, 1 test, 100 tests, whatever. At the end, you have to convince the safety authority that this area has been sufficiently explored, this problem has been sufficiently addressed.
So this is where, as NuScale went through the design certification under a more prescriptive regime with the US NRC, they can be more prescriptive in their testing.
Okay.
So the US is a little bit of a unique example because they would be more prescriptive. than say we would.
This is the consequence of the graded approach with respect to the prescriptive approach, right?
Correct. So the US has a couple of different ways you can license. One is the design certification, which is quite prescriptive.
Okay.
So in that case, they will ask us, you need to do more here, you need to do more here. In we call it their LMP, their licensing modernization project, they would tend to do less prescriptive.
Okay. Thank you. Please, one last question.
Thank you for the information. I wanted to ask that as a test facility, what are the technical challenges you face when you are testing a same component for PWR and an SMR? Like, what special challenges you have to consider while you have while testing an innovative, new advanced technology, and other than the regular PWR systems that you?
Well, actually, there isn't a big difference, I think, because when we do tests, in general, is for new systems or upgraded systems. So it is always a new component, or when the market, just a simple example. In the past, we did some tests for companies that developed steam water separators to be installed in the steam generators or DWRs, standard plants. So they wanted to optimize their steam water separator. So came to us with components. We did tests for them and did the measurements of the efficiency of separation. They came more time. So we did the tests on optimized components. At the end, they found the best they wanted, and so we completed the campaign, even if they were installed in standard plants. So from our point of view, when we do a test, it isn't, we are not going to test already existing components or already sold or operating. We are always doing tests on new things. So when we build a loop, if it is for an SMR or for a large plant, there is not much very big difference.
Thank you, Roberta. Thank you for the
We will meet tomorrow morning, Roberta, and you can see it.
presentation.